Welcome to part 3 of this video playlist about the best methods for reducing carboxylic esters to primary alcohols. This video is about reductions with boron hydrides, such as alkali borohydrides or diborane. These reducing agents are more expensive than hydrogen or sodium, but more selective and easier to handle. Most reductions won't require much optimization, and these reagents are therefore particularly well suited for quick laboratory preparations. Sodium borohydride is prepared on a large scale by treatment of trimethyl borate with sodium hydride. Reaction of alkali borohydrides with a precisely dosed quantity of an electrophile such as halogens, sulfuric acid or boron trifluoride will generate gaseous diborane or a borane ether complex if the reaction is conducted in an ether. Borane also forms stable complexes with thioethers and amines, and some of these are commercially available. Boron trihalides are more reactive than trimethyl borate, and reaction of sodium or lithium hydride with, for instance, boron trifluoride yields borohydrides at a much lower temperature. For the reduction of esters to primary alcohols, approximately 1 equivalent of sodium or lithium borohydride is usually required. When working with these reagents, one should be aware of the high toxicity and flammability of gaseous boron hydrides. Diborane is about twice as toxic as hydrogen cyanide, and borane-air mixtures are explosive over a wide range of concentrations. Diborane may even ignite spontaneously upon contact with air. Gaseous boranes will be formed upon treatment of borohydrides with electrophiles, but may also be released upon heating borane ether complexes. Borane thioether complexes are more stable and thus safer to use than complexes of borane with THF or diethyl ether. Let's have a look at some specific examples. Enantiomerically pure enolysable esters, like the starting material of this example, can racemize if the reaction conditions become too strongly alkaline. Most reducing agents can also act as bases, and the reduction of enantiomerically pure esters may therefore require some optimization. Most reductions of esters by borohydrides only proceed smoothly in methanol or ethanol as solvent. Here, the reduction succeeded in a mixture of THF and ethanol at room temperature with an excess of lithium borohydride. Unsymmetric diesters can often be selectively monoreduced if one of the two alkoxycarbonyl groups is close to an oxygen, nitrogen or sulfur atom. Here, for instance, diethyl malate was reduced once by treatment with just one equivalent of borane and THF at room temperature. This is another example of a heteroatom-directed single reduction of an unsymmetric diester. As in the previous example, no alcohol was added, what may have helped to direct the borohydride to the isobutyl ester by intermediate formation of a borate. To liberate the target diol, the initially formed cyclic borate had to be refluxed in methanol for 2 hours. Symmetric diesters are trickier to reduce only once, but occasionally successful examples are reported. Here the dimethyl ester of 3-hydroxyglutaric acid was monoreduced in high yield with an excess of borane and THF. In this example, a symmetric diester was monoreduced in ethanol with only 0.8 equivalents of sodium borohydride. No reductive ring opening of the epoxide occurred. Enolysable malonic or 3-keto esters are strongly acidic and can be difficult to reduce because enolates are less electrophilic than neutral esters. In this example, a malonate could be reduced by treatment with an excess of sodium borohydride and calcium chloride in ethanol. No beta elimination of the hydroxyl group occurred. Alpha-halomalonic acid derivatives are electrophilic halogenating reagents and therefore also difficult to reduce without simultaneous dehalogenation. Here, an alpha-fluoroester and amide were reduced selectively with borane and THF without any added alcohol, but the reaction was slow even at reflux temperature. Also, alpha-chloroketones may act as electrophilic chlorinating reagents and are readily dechlorinated by most nucleophiles and reducing agents. With sodium borohydride and methanol, however, it was possible to reduce ethyl chloroacetoacetate in high yield to the chlorinated diol. Most reducing agents will reduce ketones faster than esters. This is, however, not always the case. Some sterically crowded or electronically deactivated ketones can be difficult to reduce. In this example, one ester group was reduced selectively in the presence of a ketone and another ester by borane and THF. With catalytic amounts of cerium chloride and an excess of lithium borohydride, however, the ketone could be reduced selectively. Such chemoselectivities are difficult to foresee and must be established by experimentation. This is an example of an electronically deactivated ketone. A methyl ester was selectively reduced by treatment with sodium borohydride in ethanol. This here is another example of the selective reduction of an ethoxycarbonyl group in the presence of an epoxide. Also a nitro group and a cyano group remained unchanged. In this case, the ester was particularly reactive, and the reduction was complete after only 5 minutes at room temperature. Like halogenated ketones or malonates, also alpha-haloamides are more reactive than simple alkyl halides. With a large excess of sodium borohydride in methanol, however, it was possible to prepare chloramphenicol from the corresponding benzhydryl ester, as shown here. Allylic and benzylic halides are also more reactive than simple alkyl halides. This here is a further example of the selective reduction of an ester containing a reactive halide. To minimize the risk of amine quaternization or ether formation, the reaction was conducted in ether at 0 degrees Celsius. Alkyl iodides are also readily reduced or substituted by nucleophiles. In this example, an ethyl ester containing an acetal and a primary alkyl iodide was selectively reduced with sodium borohydride and methanol. The yield was high and no significant amount of ether was formed. So what further side reactions must be expected? Borohydrides and borane can reduce a large number of functional groups, for instance electron-deficient alkynes and alkenes, ketones, aldehydes, nitriles and imines. As shown by the previous examples though, it is sometimes possible to find conditions that enable a selective ester reduction in the presence of some of these groups. Boric acid sometimes forms surprisingly stable esters with 1,2-diols or 2-aminoethanols. If the product of a reduction contains such a substructure, a more thorough hydrolysis may be required during workup. Fluoride or hydrogen peroxide can accelerate the hydrolysis of borate esters, and the addition of a water-soluble polyol or amino alcohol may help to trap boric acid and thus liberate the target product. In this example, a borate ester could not be transesterified by refluxing in methanol, and treatment with fluoride was necessary to isolate the target diol in high yield. Some aldehydes can yield stable hemiacetals upon reaction with alcohols. If such aldehydes are the intermediates of a given ester reduction, hemiacetals may result as byproducts. Lactones can often be reduced to aldehydes with borohydrides, as in this example. Here's a list with some more examples, which you can also find in the description of this video. The next video of this playlist is about ester reductions with aluminum hydrides. These are powerful and hence not very selective reducing agents, which often require strictly anhydrous conditions. Lithium aluminum hydride is particularly well suited for reducing esters that are unreactive toward boron hydrides.